Let's take a look at the comparison between our number of folds and our sections of paper. Let's start with the accordion style. So as we compare our number of folds, let's construct a table here, to our sections of paper. Let's analyze the data that we came up with. So when we first started, there were 0 folds and there was 1 section of paper. After 1 fold, we had 2 sections of paper. After 2 folds, we had 3 sections of paper. After 3 folds, we had 4. After 4 folds, we had 5 sections. And after our 5th fold, we had 1, 2, 3, 4, 5, 6 sections of paper. Let's take a look at when we folded it in half. We have our folds and our sections. At 0 folds, again, we just had the 1 section. We had the 1 piece of paper. After our first fold, when we folded it in half, we had 2 sections. So far, it looks like our data is coming out to be the same. However, when we added a second fold, we get a little bit of a different outcome. When we folded it in half a second time, we had 4 sections. When we folded it in half again, we ended up with 8. After the 4th fold, we had 16. And after our 5th and final fold, if we look at our total number, we ended up with 32 sections. So we've seen how these two are the same. As we had our original fold and 1 fold, the number of sections were the same for both the accordion and the folding in half. But let's take a look at how they're different. For each fold, when we take a look at the change in the number of sections, for the accordion style, we see that it has a constant rate of increase of 1 each time. So we say that that has a constant difference. Whenever we have a constant difference, recall that that creates a linear function, which can be written in the form of y equals mx plus b. As we take a look at this, our y-intercept value, where its starting point is, would be 0, 1. So our y-intercept would be 1. And our slope, our constant rate of change, would be that difference, which is 1. So we could write this as an equation of y equals x for 1x, a slope of 1, plus a y-intercept of 1. We get a linear function. Now let's take a look at the halfway folds. We start off and we see an increase of 1, but then all of a sudden it has an increase of 2, increase of 4, increase of 8, increase of 16. So that one doesn't have a constant difference between them. But what it does have is what we call a constant ratio. Which means if we take the 2 values and we take the next value divided by the previous every time, we get a constant ratio. Or as you're identifying the pattern, you might see multiply by 2 every time. So our constant ratio in this case is 2. Now, our starting amount is going to be very similar. When there were 0 folds, our starting amount was still at 1. And we said it has a constant ratio of that. Folks, since it has a constant ratio, this is what we call an exponential function. Whenever we have an exponential function, it is written in the form of y equals a times b to the power of x. And sometimes you might see a plus c value in there. So what we're looking at in this time, the input variable, which is our x, our domain, is being represented by an exponent. So folks, this specific function, the b value is represented by our constant ratio. So we could represent this by y equals 2 to the power of x. So now our next goal is to discover why is it y equals 2 to the power of x? What does this function actually look like? And what does our a, b, and c values do to the function?